we turned our whole company towards attempting to land on the moon, to return the United States to the moon for the first time in 52 years.
Nova-C uses an environmentally friendly mixture of liquid methane and liquid oxygen.
Incredibly challenging thing like landing on the moon forced us to innovate.
Intuitive Machines has built an entire space program to support these CLPS missions. The company completed its lunar lander in a new facility at the Houston Spaceport, just down the street from NASA's Johnson Space Center. It's an autonomous Nova-C class lunar lander named Odysseus.
Lunar lander arrived at Kennedy Space Center in Florida back in December. Since then, teams have been integrating the spacecraft to Falcon 9's second stage in preparation for launch.
Go IM-1 and the Odysseus lunar lander.
Falcon 9 has successfully lifted off from Pad 39A at Kennedy Space Center. An incredible sight to see.
Odysseus lunar lander separation confirmed.
Our Nova-C lunar lander has successfully separated from the second stage of the launch vehicle, autonomously commissioned, and made first communications contact with Nova Control.
Our approach for landing is actually very similar to what Apollo did, which should be no surprise because the physics are very much the same.
Let's honor this momentous milestone and prepare for the challenges and triumphs that await us on our lunar journey.
Good afternoon, and welcome to NASA's Johnson Space Center in Houston. I'm Nilüfer Ramji with NASA Communications. Thanks for joining us. Intuitive Machines' lander, named Odysseus, carried 6 NASA science instruments to the South Pole region of the moon as part of the agency's Commercial Lunar Payload Services, or CLPS initiative, and Artemis campaign. The IM-1 mission is the first U.S. soft landing on the moon in more than 50 years, successfully landing on February 22nd. Joining us to provide insight on this notable mission and to answer questions, we have Steve Altemus, Chief Executive Officer and co-founder of Intuitive Machines, Dr. Joel Kearns, the Deputy Associate Administrator for Exploration at NASA's Science Mission Directorate at NASA headquarters in Washington, Dr. Tim Crain, the Chief Technology Officer and co-founder of Intuitive Machines, and finally, Dr. Sue Lederer, Project Scientist for CLPS at NASA Johnson. First, we'll start with some initial remarks from each of our briefers before opening it up for questions. We'll be taking questions in the room this afternoon and on our phone bridge. If you've joined us online today, please press *1 to add your name to the queue and ask your question. For those of you in the room, feel free to raise your hand and someone will bring you a mic. We'll now begin with opening remarks from Steve Altemus. Steve, take it away.
Thank you, Nilüfer. It's such an exciting day to be here at this time in the mission. Last time we talked, we were getting very sporadic data back and trying to understand the situation of the mission, but we've conducted a very successful mission to this point, and we expect to go to the completion of the mission as planned, with a little treat in store for us as we go forward beyond that over the next 2 and 3 weeks. I came over from Mission Control today, and the mission director for the white team in Mission Control, Jack Fisher, gave a little speech to celebrate Odie, our lander, on the surface, and what a magnificent job that robust, plucky lander did all the way to the moon and then on the surface to deliver back to NASA and our commercial companies so much data and information and science. It's just an incredible testament to how robust and like someone said, beastly that little spacecraft is. So we're really happy with that. Currently, in the Mission Control Room, Odysseus continues to generate solar power. We are projecting a time where the solar power generation will not allow Odie to continue sending down telemetry, but we will put Odie to sleep and expect to wake him up here in the next 2 or 3 weeks for a development test objective, which is actually to see if we can, when the sun illuminates the solar panel again, we get a signal back from this lander, and so we're excited about that point. Flight controllers are analyzing all the data that's coming down. We've gotten data from all of the payloads, commercial and NASA payloads to date, and NASA will talk about those. Dr. Sue will give you a rundown on what we've recovered. What we've gotten in terms of data on the vehicle is a tremendous amount of the guidance, navigation, control data, all the propulsion data, all the performance data for the vehicle that will allow us to completely reconstruct the mission and tell you all of the idiosyncrasies that went on throughout the mission, and we'll do a mission reconstruction and then evaluation on how the performance of this mission will play itself forward to missions 2 and 3 and subsequent missions. We expect that the planned mission was going to extend on the surface for 144 hours. We expect that Odie will sleep after that. We left every bit well, actually nothing left on the table. Every commodity, everything was used. All the helium was used. All the methane was used. All the power was used. And so we used up every bit of every ounce of consumables we took with us and generated on the way to complete this mission. So very excited about that. What we've done in the process of this mission, though, is we've fundamentally changed the economics of landing on the moon. And we've kicked open the door for a robust, thriving cislunar economy in the future. That's compelling. And so I think this CLPS experiment, this first landing, this success on the moon, first time in 52 years, is really a point in history that we should celebrate as we move forward to subsequent missions around the moon. We could not have done this alone. This was truly an integrated global effort, and I don't think everybody was aware of that. We returned to the moon as a commercial company, but we had multiple government agencies that we worked with. We worked with NASA, of course, and multiple departments within NASA. We worked with the FAA, the FCC. We worked with the Eastern Range, all of those to get off the ground. We then had a whole series of international partners that we used as not only our lunar data network antenna dishes on the ground, but also in the supply chain. We had Australia, the United Kingdom, Japan, South Africa, the United States dishes, and KSAT dishes, KSAT based out of Norway, in India, Singapore, Dubai, French Guiana, and Mauritius in India. The supply chain, I got to talk about a little bit from Canada, MDA and Canadensis. Sweden, AAC Clyde Space provided that impeccable power system for us on the Odysseus lander. From Spain, where we got those Thalassalinia radios that gave us the ranging tones for orbit determination. And the United States, we leveraged countless companies and their strengths in our domestic supply chain. Everyone deserves a thank you for allowing us as Intuitive Machines to take the lead and lead the United States back to the moon. It's been a daunting journey. We were met with over 11 critical mission challenges, and it was the only way to get through that was with the people of Intuitive Machines who demonstrated resilience and perseverance and triumphed in solving the engineering challenges that were put forward in front of them the whole way through the mission, all the way up until our projected end at this evening. You know, the challenges came from, people ask, you know, why was this so hard and why does it take so much effort if we've returned to the moon after 50 years? Why, and we did it 50 years ago, why is it so hard? What we had was a different kind of challenge. We were constrained in cost with a fixed price performance contract from the government. We had a schedule where we were to get this mission completed within the time it takes to get an undergraduate degree. We had a technical challenge to land softly on the South Pole region of the moon. This over-constrained environment forced innovation, and this was our first flight of this vehicle, which had never been flown before in space, let alone been designed and developed. And this was a task that was given formally to nation states and sovereign governments, and we did it as a commercial company. We did this by building a robust lunar program that could launch and land more than one time. That is in place. The Intuitive Machines operations team has been practiced now like no other and can handle the challenges that are thrown for flying in space. We communicated in a way that not everybody was necessarily satisfied with. We learned in our communications. But what we tried to do was diagnose a problem and develop an approach, and then communicate what our approach was going to be and how we were going to solve it that was going to improve or maintain Odie's health along the way. And I think we did that, and we did that effectively, and I'm proud of the communications team for what they have done. You know, data flows out of mission control in a very sporadic way, whether communications are happening in rapid pace and near real time, or they're delayed over the weekend because we're struggling with getting our telemetry down into these big dishes around the world. But every time we reported out the status of where we were. We've assembled the best and brightest in the company that I can imagine, and trying to create a business that's a national asset for the United States, and hopefully feed the lessons learned into IM2 and IM3 and our subsequent missions. I have a few very fascinating images for you that I can talk through now if you look up at the teleprompter. This is a picture of Odie on the surface of the moon, touching down with its engine firing. You see here the landing gear piece is broken off there on the left of the image. The landing gear did what it was supposed to do and protect the lander as it landed on the surface. The engine plume interaction with the surface gives us this excellent view of how the ejecta, the regolith, moves away from the plume interaction. There's scientific information in that data right there. What you don't see in this picture is that we landed, our navigation system landed us with precision and landed us softly on the moon. The shock absorbers took the load, and the lander now tilted over gently, and we think it's about 30 degrees, and communicating all the way down to Earth. And I think Tim is going to give you an estimate of how much data we've actually brought down. There's a little image in the center of the white patch on this. That's an American flag. I want to highlight that that American flag was a donation by NASA and is from 1970 in the Apollo program, and it was a certified piece of flight hardware. And we took that American flag and we proudly put it on Odysseus and carried it to the moon like it should have been done 52 years ago. So I'm really proud of that. Next picture. This picture shows the fisheye lens kind of view of, and all of the data that's within how we're able to give you the images we have. All the data is there in this wide-angle view. Next image. And here we are, how Odie conducted the brilliant 6-day mission on the surface. You see the gold foil blanket is the helium tank. You see that we're tilted over slightly, still more upright than we initially thought. We did land upright, we captured data, and then we tilted over slowly in about 2 seconds and came to rest either on the opposite helium tank or a computer shelf, and we're able to communicate, get all 6 payloads data back, plus all the commercial payloads, and continue to transmit as we go forward. Brilliant performance by a small lunar lander and a brilliant commercial company called Intuitive Machines. Thank you, Lederer.
Thank you, Steve. We'll now hand it over to Joel. Joel, you're up.
Hey, thank you, Lederer. So first, again, I want to again congratulate Intuitive Machines for this mission of many firsts. We mentioned many of them on Friday, but I want to talk again about the fact that this is the first time in the 21st century that an organization in the United States has landed equipment on the surface of the moon, and we're getting data back from that equipment, engineering and science data. It's an exciting time to be on day 6 of this new era in the 21st century. Now, a soft touchdown on the moon is a great accomplishment. This morning, in response to a question, our administrator of NASA, Senator Bill Nelson, in response to a question about does NASA consider this mission to be successful, said yes. This mission is a pathfinder. You can think of it as a flight test, a first step to get back to the moon, a pathfinder both for the more complicated and sophisticated robotic science landing missions that will occur in the future, and a pathfinder to get data for taking our human explorers back to the moon and to places on the moon that humans have never been before under Artemis. This also provides evidence for the first time that the Commercial Lunar Payload Services model, that is, that NASA could go out and purchase as a service, taking equipment to the surface of the moon and getting data back from the surface of the moon, can work. And it's the first time that we now have that evidence. It's also a soft landing at an extreme lower latitude on the moon, 80 degrees south, near the South Pole region. And I want to point out why this is so different, because as others have said, we get questions periodically that since Americans did land on the moon in the 1960s, and we haven't been back in a long time until setting on this new road of getting science and technology on the moon, why is it really that difficult? And I want to remind folks that, and again, what you have to do to get down to the surface of the moon, since there's no air on the moon, is in effect you have to ride a rocket all the way from the fast speed of being up in orbit all the way to practically no speed at a predetermined point on the surface at a predetermined elevation that you're trying to get to. And in effect, you have to bring down with you on the rocket all the fuel you need to slow down. So this is a very, very complex undertaking. And when we established the first set of CLPS landings, the first initial ones internally at NASA, we discussed that the major goal was to soft land and get some amount of data back from our scientific and engineering investigations. And we can clearly see that we did get our cargo to the surface of the moon, and we have gotten data back, as project scientist Sue Lederer will talk about in a few minutes. There's also a lot of learning that comes out of this attempt. First flight of this new type of vehicle, Nova C, much of which Steve Altemus already touched on in his introduction, but also a lot of learning about orbit determination and use of commercial communication systems around the world. And I would like to point out that there were a number of organizations, as Steve said, that Intuitive Machines reached out to get either assistance or advice or information during the mission. We talked last Friday about Intuitive Machines' use of the onboard payload, the navigation Doppler LIDAR from NASA's Langley Research Center. But also there was close coordination and data from the payload Lunar Node 1 from NASA's Marshall Space Flight Center. There was a lot of support when requested from our Space Communications and Navigations program at NASA, in particular our Deep Space Network administered by the Jet Propulsion Laboratory in California. And also you will have noticed in the news that our Lunar Reconnaissance Orbiter, a NASA imaging spacecraft, did photograph the touchdown location of Odysseus on the lunar surface. And that required a lot of work by the Lunar Reconnaissance Orbiter project at Goddard Space Flight Center, the Lunar Reconnaissance Orbiter Camera Project, principal investigator located at Arizona State University, and others. Many of those elements together, although mostly you're hearing about CLPS with this mission, LRO, the scientific instruments we provided, and CLPS overall as part of NASA's Lunar Science Program, or the Lunar Discovery and Exploration Program. Again, this was a Pathfinder mission. There's going to be a lot of learning that comes out of it when the mission is concluded, both for the company whose mission this is, Intuitive Machines, and also for NASA as we look back how we operated during this mission. And now we're looking forward to the future CLPS landings coming up for Intuitive Machines. That'll be Intuitive Machines Mission 1. Will it take to the surface of the moon, again to the South Pole, NASA drilling and chemical composition determination equipment for our Space Technology Mission Directorate. And I'll turn it back to you, Nilifer.
Thank you so much, Joel. Next up, we have Tim. Over to you.
Thanks, Nilifer. Some appreciations that I would be remiss if I didn't offer up. First and foremost, as Steve said, our people, the amazing team of mechanics at Intuitive Machines. It is an excellent team, but it's also very efficient. We could not have done it without all of them. Every person was essential. And then behind them stands a network of family and friends who have sacrificed over the last couple of weeks to support us through some long hours and through some very exciting times on orbit. I would say NASA, not only for the moral and great technical support, Joel, that we've gotten in mission from DSN and from some of the payloads, but also for the vision going back for programs like Morpheus and ALHAT, which established the technology that was the foundation and the concepts that we wove into Odysseus as a lander. SpaceX was a great partner working a very complex problem of fueling a cryogenic payload at the Cape. Our commercial payload customers for having faith in us. This is something that had not been done before. and they believed in us to see that we could pull this off. And then our LTN partners, we had people on the phone listening with the most delicate instruments from Cornwall, from Kentucky, New South Wales, Okinawa, Bangalore, Karoo, Heart of Beastock, among others, and really felt like we were part of a global team as we found a way to reestablish science and data communications with Odysseus on the surface of the moon. There were a number of firsts on this mission. We're particularly proud of our cryogenic propulsion system. This was the first time, again, that a cryogenic payload has been fueled on the pad. The first time a flight of a composite overwrapped linerless cryogenic tank has been attempted and succeeded. The first time a Methalox engine has been fired in deep space, fired repeatedly in deep space. We enjoyed the fact that we set the record for length of an engine firing with our lunar orbit insertion, and then broke it the next day with our powered descent. So that was good company to be in, we thought. It's a deeply throttling engine. We used thermodynamic venting systems for cryogenic cooling, inline processing of optical imagery, which enabled us to land safely, and then we collected a ton of multipath data from the lunar South Pole region using our multiple antennas and radios. There are 4 things that we could not test before launch. We tested every system in part and in whole where we could. There were 4 things we could not test, and that this flight was going to validate for us. We could not test a fully loaded liquid oxygen, liquid methane vehicle through launch loads and vibes. No such facilities exist. You have to do the analysis, and you have to launch to see if your design holds. It does. You cannot test the free flight control of a main engine in 1G, 1 Earth gravity. You have to do that in space, and we did that with our commissioning maneuver and our trajectory correction maneuvers. We could not test our lunar telecommunications network with our radios at lunar distance. We simulated it, we emulated it, we had to actually go into space to do the final test. And then we could not test our camera performance at the moon unless we were there. These were the 4 critical challenges as Chief Technology Officer that I knew we had to overcome and we had to demonstrate proficiency in. And I'm proud to report that we have checked all of these off, and we have a strong foundation for Intuitive Machines Mission 2, which will be coming up later this year. What does the future hold? Number 1, more cameras. The message is loud and clear. We need more cameras. We have that in the works, so more great imagery from the moon. IM2 and IM3, we have a commercial mission called IMC1 in the works. We're working on a larger lander called Nova-D, and we're working on our own communication satellites around the moon to enable business for ourselves and for other lunar explorers. I would like to talk a little bit about the ops dynamic, just to give you a little bit of insight into the room. It changed after we land. Prior to landing, we had 3 shifts and a team 4 who were very focused on the flight dynamics and control of a vehicle. Eyes were very much on the monitors and the consoles in front of you. Once we landed, we moved into how do we maximize the value of this asset for ourselves and for our customers. And the Ops Center became a swarm of activity. Just yesterday morning, we were in our high data pass over Parks in Australia. We had 3 mission directors in Nova Control. One was focusing on pulling data down and managing the power and health systems of Odysseus. The other was working on bringing the Scalps payload online so we could extract data from that payload, and Sue will talk more about that. And then the third, myself, we're working on getting the Eagle Cam up and ready for ejection. So it really was an all hands on deck. Let's maximize the time we have available on this asset while we can, and I think we've done an incredibly effective job. And as of the time I came into this briefing, we had brought down over 350 megabytes of science and engineering data on this mission. Nilüfer?
Thank you, Tim, and thanks for sharing that wonderful data point. Sue, it's your turn. You're up.
I feel like I get the most exciting part of it, though I'm sure that IM won't agree with me. But I've been working with all of the NASA payloads for the last 3 years. I've had the absolute privilege to work with amazing groups of people who have really stepped up to the task as we've really encountered challenges in using these NASA payloads. But we've all worked together as a team, to my CLPS operating team, everybody really stepped up and helped a lot. So teams, collaboration, people, this is really what it's about. And so I want to make sure that the teams themselves all feel really good about everything that they've done for us. So the data that we've collected has come in a number of phases. During transit, we were able to operate all of our powered payloads on transit. On descent and landing, our navigation Doppler LiDAR NDL was able to collect data that will help us to land safely in the future. And on the surface, the 3 payloads that were planned to operate on the surface have all been able to collect data. So I just want to take a little bit of time to go through each of the payloads to try to really help you to understand what we've been working on. LN1 is a navigation and communication beacon that transmits radio signals back down to the Earth. They were able to complete 4 passes with Goldstone and Madrid, and 2 more passes to the Madrid ground station on the surface. So we mentioned earlier that LN1 has really stepped up to the task when IM came to us and said, hey, we really could use some help with navigation information. So I was in the car on the way home after pulling a triple shift. Sorry, Joel. And and calling the LN1 PI, and I said, hey, Evan, is there a way that we can get your help with the navigation and working with the DSN? And he so calmly and coolly said, we're a navigation beacon. We're here to help you navigate. And that's what they did. So very proud of that team. ROLS's is the next one, and this is the radio wave observations at the lunar surface of the photoelectron density sheath. They have 4 antennas that were planned to be deployed on the surface. And Odie had a little surprise for us on the way with a little bit of help from the sun, creating a little bit more heat than we expected for the frangible. We did pop one of the antennas as we were in transit. And we took that as a sign that we were ready to start collecting science data, and why not take that opportunity? So while we had not planned to operate ROLS's at all in transit, we were able to get not only checkout data, but a fair bit of science data with that antenna that we hadn't planned. So a little bit of bonus science. Thank you for that. So we're very happy about that. The remaining antennas were deployed on the surface, and we were also able to collect science data with those antennas deployed as was expected for that payload. Just a couple of notes from the ROLS's team that they have just started downloading this data in the last few days, and already they can tell us that they have detected frequencies of radio noise from the Earth, but the indication is that the lower frequency data, Earth is a lot more quiet than they expected, below 15 megahertz, but at the higher frequency, the Earth is definitely shouting out a bit. So, and their observations are also consistent with a radio quiet sun. So they're already collecting and really analyzing this data, and we have now downloaded additional data that we've collected just as we were getting ready for this brief. So we have all the ROLS's data down. SCALPS is the stereo cameras for lunar plume surface studies, and their goal was to detect the plumes being ejected and creating surface plumes or surface interaction plumes with the engine on the way down. We unfortunately had some hardware problems that did not allow the SCALPS instrument to operate during descent. However, one of the SCALPS team members, shout out to them, came up with an idea to potentially do some troubleshooting. And just 2 days ago, with very little sleep for all of us, the IM team was able to work with us very collaboratively in figuring out how to change how we were collecting data with the SCALPS instrument so that we were able to operate SCALPS from the surface of the moon just this morning. So a lot of people working a lot of hours, and a shout out to the SCALPS team for all their dedication in helping us and helping IM to figure out a way to get SCALPS to work. NDL is the navigation Doppler LiDAR. It's for precise velocity and range sensing. We've talked about NDL and what they've been able to do. They are designed to help safely navigate a vehicle to the surface. All of the NDL data has now been received, and NDL reports that their instrument has worked far better than they expected, so we're very excited to see the final data outcomes from NDL. RFMG is a radio frequency mass gauge. They were able to collect data while we were tanking on the surface here on the Earth before we launched. as well as loading those propellants on the launch pad, also during coast in the zero gravity of environment of space that this allows us to do. It's very hard to do that if you don't have gravity pulling down your propellant, as well as during descent to the surface of the moon, as well as in lunar orbit. So we collected a lot of data with RFMG, and this is the first time that RFMG has been integrated into a propulsion system. Their results are really going to help us with guiding the future improvements of technology and integration for future Artemis missions, both to the moon and hopefully to Mars as well. And then finally, the LRA is the Laser Retroreflect Array, and we've been doing some talking back and forth over the last 6 days to figure out whether or not it was possible to range to the retroreflector. And hearing from the PI of LRA, we do believe that the NASA LRO is going to be able to use their LOLA laser altimeter to range to LRA. So we will be working on that in the coming months, and very excited to have a location marker on the moon at 80 degrees south, so that this is going to be great for navigation in the future. So I know that Joel said that we've had 6 days, and I would actually say that we've had 13 amazing days. So we are at lucky number 13. In the first few days, we struggled to get communications, but the perseverance of the IM team, just not willing to give up, working with us. And as Steve noted, as soon as we landed and we started getting into what are we going to do and how do we do this, their team pulled us. They came down to our NASA back room and said, we need to work this. Come work with us, and pulled us all into mission control. So we were collaboratively working together to find solutions so that the spacecraft could live, the payloads could get their data. And instead of ending up with a few bytes of data, which was the baseline goal for us, we've gotten over 50 megabytes of data, which we went from basically a cocktail straw of data coming back to a boba tea size straw of data coming back. So we're all very excited now that we've gotten a lot of data back from the surface of the moon. So again, a shout out to the collaboration of the teamwork from the payloads, from the CLPS operations team, from DSM, from IM. We've all worked together. It's the people that really make a difference and make sure that we go from how do we overcome challenges to how do we have this incredible success. And that's where we're at today, is with incredible successes for all of our payloads. Back to you, Nilüfer.
Thank you so much, and thank you for all of our briefers for their comments today. What we'll do right now is open it up for questions. So for those of you in the room, just raise your hand and we'll bring a mic over to you. And if you're on the phone bridge, please dial *1 to get your name in the queue to submit a question. Once your name is called, please state your name and your affiliation and to whom you'd like to direct your question. If you find that your question's already been answered, please press *2 to withdraw it. Let's kick it off with Gina Sinceri.
I'm going to start with Steve. You said 11 points was kind of do or die. Could you tick-tock for me what those 11 points were?
Yeah, I'll defer that. I have that. I'll defer that to Tim, who's got the technical background to talk of those in a little more detail.
Yeah, there were a number of things we had to overcome, and some of them actually, Gina, began before flight. So we had warm methane on our first day of flight, and we had to work with SpaceX to adjust that and get ready to go for the second day. And so we overcame that. I think we published the Star Tracker issue, which was we had too tight of a tolerance check on a numerical condition for the measurements coming out of the Star Tracker. That prevented our vehicle from staging all the way to a sun pointing power positive. So we had to patch the interface with the Star Tracker to fix that. If we don't fix that, the mission ends very quickly, but the team was very effective on that. Another one that probably ticks off a few of those, we discovered in our commissioning maneuver that we had a drift in the yaw channel of our main engine control. So if you'll hand me micro Odie. During a main engine burn, the way we steer the vehicles, we actually gimbal the motor, and so you turn it one way and it helps provide control on these two axes. We were drifting to one side during the commissioning maneuver, and then we saw it again in TCM-1. So what we had to do to troubleshoot that was to come up with scenarios where our engine geometry understanding and control would lead us into that drift. We knew we could do the small burns, but it was not going to be sufficient for the longer burns of LOI and power descent. So we did a couple of troubleshooting steps there. One was we moved the CG estimate on the vehicle around, which we suspected wasn't really the case, but it mimicked the signature we were seeing. And then we did a patch to our engine geometry, which was what we call an iLoad set, or parameters that the software reads kind of from a flat file. We updated our iLoads to redefine the engine geometry because we began to understand that under full thrust load, the geometry of our actuators was slightly different. And so we're able to patch that, and that led us to the successful LOI and the successful power descent. I will tell you that on the day of landing, when we watched the pointing control come across the consoles, it really looked like a video game. It was so good. I had never in any of our simulations seen the engine perform as well as it was after we had tuned it up through those burns. But if we hadn't done that, then we would not have been able to land on the moon. So those were some big steps for us. We published a few things about learning how to chill our engine in. We do have a cryogenic engine. We have to chill the metal of the engine itself before we can fire the engine. Our first commissioning maneuver, we didn't get it right on the methane side, and we had to try again, and we fired successfully, but not on time for the commissioning maneuver. We came back and reloaded for our first correction maneuver, TCM-1, and we missed the other side, the oxygen side. I may have them backwards. We missed oxygen on the first one, we missed methane on the second one. And we had to reload, and a couple hours later we came back and we dialed that in. From that burn on, though, we had it perfected. And the next 5 burns, the process that we tuned once we were in orbit, we hit all 5 burns exactly on time of ignition. If I get to the moon and I miss LOI by even a minute, we don't land on the moon. It's very, very precise. So that was another one we overcame. We did end up in a lower orbit after LOI than we'd anticipated. Our paraloon was low. And fortunately, our flight dynamics engineers had preloaded the ability to do a lunar correction maneuver, and we were able to push that up and move our orbit from our planned lunar orbit, which would be 100-kilometer circular, basically into something very close to our descent orbit. So effectively, we had the agility in our control room to move deorbit insertion from orbit 12 to orbit 3, something like that. What else do I have on my list? Oh, we discovered that the laser rangefinders weren't working. Again, it was an interface issue, and we've talked a little bit about that. You know, there's a pin in the cable that's a safety feature that once you put it on, you can't see if that pin's in place or not. And it's a Type 4 laser, so we didn't test it once we got to the Cape. Clearly something we can fix and rectify in testing on the next time through. And nonetheless, the vehicle performed just with our optical navigation system above expectations and allowed us to land safely. And then there were a number of other things that probably don't rise to the same level. And a lot of these things were crises anticipated, identified, and resolved before they impacted the mission. And so the team was excellent in saying, okay, if this is the challenge we're faced with, this is the resolution, and how do we marshal our resources in that control room and with our backup Team 4 to make sure they did not impact our ability to land safely.
Thank you so much. We have another question in the room that we're going to take.
Hi, Eric Berger with Ars Technica. First question is for Steve or Tim. Can you describe how the lander came to be gently landing on the moon? I guess it's only about 30% tipped over. Do you think it's leaning against a rock or something's holding it up? And then, Joel, I'm interested in sort of your assessment of the mission in terms of the objectives NASA hoped to see from the soft landing to getting all the data back. Was this like 100% mission success from the CLPS program's perspective, or how would you sort of grade it?
So with respect to piecing together what happened at landing, we received telemetry. If you remember, on the evening of landing, we had no communication signal and then a weak signal. And in our consoles, the data was up to a point and then frozen until that communication was restored. So we had an indication that we had landed and we were upright with that stale data. And when we came back and looked at it. When we restored the communications, we noticed that we were getting the IMU telling us we see gravity more in the Z direction than in the X direction. Well, then we did a reconstruction where we actually calculated, based the trajectory, and the flight dynamics guys calculated that we actually came down just short of our landing site at a higher elevation than where our landing site was going to be. About a 1.5 kilometer difference between the ellipse of uncertainty for our landing and where we touched down. That elevation was higher, so we came in with more downward velocity, and we came with more horizontal velocity. And so we hit harder and sort of skidded along the way. And we see that disruption in the regolith from the LRO data that we've been able to get from LRO and ASU. And that discoloration says that we came down with the engine firing because the automated flight manager had not moded to where it was trying to sense and shut down the engine. We saw a spike when we touched down in the engine combustion chamber. That was like if you shut off the full thrust by landing on the surface. So we know the engine belt contacted the surface. The landing gear took the bulk of the load, and we broke one or two possibly landing gear. And so we sat there upright with the engine firing for a period of time. And then as it wound down, the vehicle just gently tipped over. And in our simulation with 1/6 gravity, we showed that it took about 2 seconds. And we landed on a 12-degree slope. And then that 12-degree slope, compounded with a helium tank underneath or a radio shelf, would put us at an angle that's approximately 30 degrees off the surface. And we have that photo now to confirm that's the orientation. We also know the roll orientation when we were going to set the high gain antenna towards Earth and the solar arrays for the sun. We know that roll worked, but we know when we landed, the top deck solar array was shadowed, and we weren't generating power with the top deck solar array, so we got that orientation right. So those were all the parameters that had to unfold over time to get us a good understanding of where we came. And then just today, we have this picture of us leaning gently on the surface.
If we can pull the picture up, oh great, you read my mind. The LRO image, if you look at it, there's a large crater not far from where we landed. If you look in the middle of the picture, you see there's kind of a dark band. That is that crater. And so the beginning of that dark band is the shadow into that, what Mark Robinson from ASU tells me is probably a 2 billion-year-old crater. And the first edge of that darkness is about 500 meters from where we are. And then the ridge beyond that is another 500 meters, so about 1 kilometer away. And then you can see kind of a light band just underneath the helium tank, which is the lunar surface on the far side of that crater. So that'll give you an idea when you look at the picture of how we're oriented. In this picture, the sun is to the right and is moving across the sky right to left. And so it's illuminating the solar array on the other side. And you can kind of get a feel for that 30-degree, let me see if I can get this right. So the camera is kind of here, and it's taking a picture down between the legs. So we're about at 30 degrees on a 12-degree slope, landing like that. And that's how we get to 30 degrees. Earth is off in this direction, and so our antennas are in an off-nominal configuration. The reason some of this data took a while for us to get to is we had to really work with our in-network lunar telemetry partners, and then also with DSN to figure out what this strange environment was. Absolutely, our signals were bouncing off the moon. So we were receiving both the direct path signals from our radio and the opposite polarization as well. And so we had to sort through exactly how to do that. But once we got it down, we got into a rhythm where we could monitor health and send some basic commands for about 16 hours a day. And then we'd come over Australia, and we were able to really pull down data for about 8 hours at a time. And that was intense. That's where we had everybody in there. We had no dead air, just like in the radio business. There was no dead air, right? We wanted data coming down all the time. Well, I want to fix this payload. I want to work with scouts. Great. Be downloading data while you're working with scouts. And so that was kind of the operation we had. I know that wasn't your question, but I just wanted to talk about it. So, sorry.
I can answer your question you had about how we feel about mission success. We don't have a quantitative number to give. As I said earlier, from a CLPS point of view of demonstrating the model, our goal for the first set of task orders called Task Order 2 The big goal was to land your equipment softly so you could get data from it after you land, and that was done successfully. We also identified objectives that we had for each of the science instruments, and we're assessing based on the data collected to date and how that was influenced by the landing attitude, how we did. For example, Susan Lederer mentioned that we planned to take images from scalps on the way down to look at the interaction of the rocket plume with the surface. We know that we didn't do that. But we're fortunate that several of these instruments, like scalps and Rolls, will fly on future CLPS deliveries also. So we have an opportunity in the future to take that data on different vehicles.
Great. We will now transition over to our phone bridge to take additional questions we have, and we'll kick it off with Marcia Dunn with Associated Press. Marcia?
Oh, hi. Hello. For Steve, please. How much time does Odysseus have left? How many more hours do you anticipate? How will you know for sure that it's the end? And are any eulogies planned for when the lander falls silent? Thanks.
Well, I think what we're going to do is kind of tuck Odie in for the cold night of the moon and see if we can't wake him up here when we get the solar noon here in about 3 weeks. So we know through that we are degrading in power, and we expect that within about 5 hours or so from now is when we will be at a point where we will no longer have commanding or telemetry coming down. We are going to leave the computers and the power system in a place where we can wake it up and do this development test objective to actually try to ping it with an antenna and see if we can't wake it up once it gets power again. So that's the plan. And if you recall, the whole idea of this mission was not to live as long as you could on the surface. This mission was intended as a scout and a pilot mission to go land on the surface, collect the data, and then the cold of night was going to take the lander where it would sit there quietly for the rest of the time. We accomplished that. And so now, extending to get additional data beyond that planned mission end and quiet power down of Odysseus, we expect that there may be another opportunity here in a couple of weeks to take a look at it again. So no eulogies planned, Marcia. Only celebration and cheering.
Thank you so much for that. Next up, we have Joey Roulette from Reuters. Joey? All right, we do not have Joey Roulette. We have Andrea Line. Oh, there we go. Okay.
Can you hear me? sorry, I didn't know I was on mute. Question for Tim or Steve. I'm just curious what you think the chances are that you guys will be able to wake it up after that lunar night, since that wasn't part of the mission goals, right? And what does that hinge on? What do you guys want to see? And then I guess for Steve, how do you ensure that other companies are aware of the problems that you guys faced? Are you looking to share the lessons learned from this mission with Astrobotic and Firefly, maybe? Thanks.
Well, I can address the surviving the night. You know, the real limiter, the number one limiter we face is the batteries. Batteries are a chemical asset. That chemistry does not respond well to deep cold. And so if something happens to the batteries for 14 days of less than 250 degrees, then we won't be able to come back up. And the batteries absolutely are not tested to that level of cold. Neither is our flight computer or our radios. If we asked our vendors to tell us what the probability was of surviving the deep cold of the moon, they would not put it in writing, and so well, they shouldn't. So those are the things we're worried about. Our solar arrays should handle that fine. So we're confident that when the sun comes back up over Odysseus, that the solar arrays will energize and they'll send power. The real question is, are the batteries there to receive that power and pass it on? And then will the electronics within our computer and radio have withstood that deep cold and not basically cracked under the thermal stress? So wouldn't put odds on it, but those are the things we're facing when the sun comes back up on the solar array in a few weeks.
Yeah, and for my comment there is we're in a position where why not try, you know, with no odds on it. let's see what happens and gain some data and insight that we otherwise wouldn't get if we weren't on the surface of the moon.
We've also overcome challenge after challenge after challenge we didn't know that we would be able to get past. And he's a scrappy little dude.
Yeah, I would not bet
I
against
have confidence
Odie.
in Odie at this
Yeah,
point.
that's right.
It's been incredible.
As far as sharing the data with other industry vendors who are attempting to land softly on the moon, also, we certainly want to give them the insights of our learning and our experience. And I think there's a whole series of conference papers and talks and briefings on what we experienced and what we learned that are part of this historic journey that we want to share. We want to share and talk about and let people know so that we raise all boats and we all end up building this burgeoning cislunar economy.
Great, thank you so much for that. Next up, we have Andrea Leinfelder with the Houston Chronicle. Andrea?
Hi, thanks for taking the questions. This is for Steve or Tim. Can you share a list of mission objectives and which of these were met and which were not? Also, can you explain a little more why you could pull more data when over Australia and not at other times? And then for Sue, so all 6 NASA payloads received data, but what was the quality of this data? Was it the quality expected or was it limited by the lander tipping over? Thank you.
Well, I think we had some very high-level mission objectives, was to touch down softly on the surface of the moon, softly and safely, and return scientific data to our customers, the 2 primary objectives. And both of those objectives are met. So in our mind, this is an unqualified success. I think internally, we had objectives to really wring out the performance of this vehicle and understand that the engineering process we went through from design to development to testing and assembly, integration, and integrated testing was that model in the way we did our aerospace engineering was that solid thesis and a solid model. And in fact, it was, because this spacecraft is such an amazing spacecraft that we did fixed price in a short amount of time that was able to perform everything we asked of it. So I think those are my top 3 mission objectives. Tim, any insight on others?
Yeah, with respect to why over Australia, we do have our network of dishes that range anywhere from 18 meters to 32 meters, except for the dish in Parks Australia, which is part of CSIRO, and that's the dish. They made a movie about it called The Dish. It's a 64-meter dish. Now, it can only receive, but it has a very sensitive ability to detect radio signals. And we were transmitting not through our high gain antenna, we were transmitting through a Omni antenna about the size of this water bottle. And that's what we had to transmit. And oh, by the way, it's not pointing at Earth. And so the way our engineers were able to work with the engineers at Parks to pull that data down was fantastic, but we could only do it when we were within the physical limitations of the Parks dish to go horizon to horizon. Oh, by the way, when you move a 64-meter dish, if the wind kicks up above a certain level, it stops. And so we all of a sudden became hedge meteorologists trying to predict what the winds would be like during our data passes. But I really have to give it to the team in Australia. They did a fantastic job allowing us to get this critical data down.
You also posed a question about what was the quality of the NASA instrument data that came back. I'll turn that over to Susan Lederer to address, but I'll point out that part of the goals for each instrument on this initial mission were to make sure that the instrument functioned, that it was fed power, could pass commands into the instrument data back to the ground. You could think of that as kind of operational demonstrations. Then there would be engineering data that the instrument would take, and then finally there would be the measurements that would be taken that you could think of as being the science that comes out of the instrument. So Susan, could you say a few words about the quality of the data that you've seen?
Yeah, absolutely. And it of course depends on which payload you are working with. Some have gotten more data, some have gotten all the data that they were hoping for. Bottom line is that every payload has met some level of their objectives, and we're very excited about that. Joel mentioned that we have tech demo instruments that are on board. They have now graduated to have actually been navigation instruments that I worked with IM, helping them to land safely on the surface, both LN1 in transit as well as NDL on descent. So we're very proud of our payloads. We're very excited to start pouring through the data. And in fact, on my way here, I was listening on the loops as data was being downloaded just hours before, and in fact, just before we walked into the press briefing, indicating that all the data that we've taken is now on the surface. So our payloads are very excited about being able to now analyze this data. So I want to give them all a chance to rest first, and then we'll get into at what level have we succeeded. But everyone has succeeded at least in some of the objectives.
So I have a question for Sue and Joel. If Odie wakes up in 2 or 3 weeks, do you want to turn your sensors back on?
Absolutely. The scientists always want more data. More data.
We'll give it a try.
As do the engineers. Great.
Great. Thank you guys so much for that. Next up, we have Chris Davenport with the Washington Post. Chris?
Hey, all. I guess for Steve and Tim, I was just curious if you could talk a little bit about that safety switch, which you, I think, said was sort of like the safety of a gun, and it wasn't switched to enable. Just curious what happened there, how something so important could have been overlooked. And then for Sue, a quick follow-up on what you were just saying. On the Scouts instrument specifically, if it was not working during the descent, if it only started working 2 days ago, were you actually able to characterize the dust plume that was kicked up by the engines if it wasn't working then? I'm just sort of curious if you are able to get a sense of how an engine will interact with the lunar surface and disturb it, if you'll actually be able to sort of perform that analysis. Thank you.
Chris, for your first question, we have a difference between the engineering development units that we use on the ground for the laser rangefinders and the flight units that were on the vehicle. When we tested the laser rangefinders on the ground, the engineering units did not have that safety enable switch, if you will. When we tested the flight lasers on the ground, we had ground support equipment feeding the power to those units. In those cables, there is a wire that pins into a connector that provides power to disable that safety enable and allow you to fire that laser rangefinder, and we did that, and it worked. The flight cables, however, did not have that wire lead in them, and so, you know, there's a range safety requirement that you do not have an active laser with a potential to fire it, and you needed a limiter while you're on the launch pad getting ready to launch. And so that's why that safety enable is in that box, one for ground safety, one for range safety limits. And so there is a difference between how we test on the ground and the units we tested and the cables we used versus the cables we built for flight. And that one wire in miles and miles and miles of wiring on the vehicle and different harnesses was an oversight. And we missed it, and we're not able to command that disable switch on, and therefore didn't have the laser rangefinders. And so a couple of people beating themselves up pretty bad, but the fact that we were able to land softly using optical measurements is just a breakthrough in the performance of this vehicle. So, hey, if we missed a pin out of 3 miles of wiring and 10,000 pins and connections in the connectors, I'll take that all day long.
To answer your question about Scalps, you are correct that because we were unable to collect data on the way down, we know that there was a hardware failure that we fixed in the serial port after we were on the surface. We also didn't trigger in order to, even if that had been working, we didn't have the triggers that were available that were necessary to collect that data on the way down, is my understanding. And so we were not able to collect the data for the plume surface images that Scouts was to take. However, a couple of upsides is that not only were they able to meet some of their minimum success criteria, surviving launch, completing transit checkouts, they were able to do a transit checkout on the surface. And this is important for them because there is another mission, as Joel mentioned, the Firefly mission that's coming up later this year has another version of Scalps, so they will be able to use that data to better plan for what to do for Firefly. And then in addition, there were certainly images that were taken by the other cameras that were on board. And just before this conference press conference started, we did hear from Intuitive Machines that they are absolutely happy to share those images that they collected with their cameras. We have seen some of them, and we see some of the plume coming up from the surface, and they are willing to and very happy to collaborate with Scalps to share those images so that Scalps can use that data to do some analysis of the plume surface interaction between the engine and the dust on the lunar surface.
Lots of real-time updates we have today. Next up, we have Micah Maidenberg with the Wall Street Journal.
Hey, good afternoon. Just first for Tim, how many of the 11 kind of critical moments that have been discussed, could have caused a mission failure? Is that all of them? I think you said some were a little bit more serious and some were a little less serious, as I understood it. And then Steve, I'm curious, given IM-1, if the mission has generated new deals or interest from commercial customers or non-NASA customers for future landings, or if not, how you're thinking about pursuing those, given the mission so far. Thanks a lot.
Yeah, great question, Micah. One thing I'll say about some of these critical events that we solved going through the mission, they didn't all have the same time constant. So patching the star tracker was something that had a definite immediacy to it, because if we don't get that fixed, then we're going to run out of power in a matter of hours. The challenge of making sure that we had our engine start sequence was one that we had opportunities built into the mission to resolve that as we went. So if it had gone uncorrected over the course of the next 4 burns, then mission success was not assured. But we had opportunities built in to resolve it as we went. So the time constant on that was a little bit different. The same thing for fine-tuning the engine geometry and making sure we had the steering coordinates updated for what we were actually seeing in flight. So it was kind of a mix. If any of these issues are left unresolved, they become major. But not all of them were critical in the sense of, I need to solve them in the next couple of hours or we're in real trouble. With that said, this is a sprint mission to the moon. We did the fastest transfer from launch to low Earth orbit that anyone has done since 1972. And you definitely felt that pressure of, I only have so many days and the clock is ticking to get myself into lunar orbit. So I wouldn't necessarily say that we breathed easier on the ones that we knew we had a little bit more time for, because they were critical. But I do want to emphasize that the time constants in these were variable.
Yeah, the one thing I'll add to Tim's question, or the question he just answered, is that about 3 days into the mission after launch, we said to ourselves, we got the mission directors together and the Team 4 leaders together and said, look, we've got to get on top of this. There are things that are happening to us and we're in reactionary mode trying to make sure we save the vehicle. We've got to be looking ahead and anticipating what might happen downstream. So as we went through the mission, we got further and further ahead, thinking about the possible failures and what could get us and what we had to fix in that certain time frame. And once we did that, I think we really had ourselves in the right mind frame to succeed. So, and on your other question, Micah, is that we have been contacted. I think the ESA contacts that we have and representatives we have, we're very excited for our mission. And we've been talking to a number of European companies that are flying equipment on our mission too, and ESA expressed interest in wanting to participate with us in flying payloads on that mission. We've heard from several companies who wish to entertain sponsorships, so that's of interest to us. We haven't had those conversations yet other than their outreach to us. And so I just think it's the tip of the iceberg and it's beginning for people to realize, wow, this was an incredible success. What are the possibilities? And I think that was the whole purpose here, was to open up space exploration to be everyone's. And so more and more people can participate. And if that's the result we get, I'm happy for that.
Great. We have quite a few questions we want to get through this afternoon. So next up, we have Jeff Faust with Space News. Jeff?
Good afternoon. A question for Tim or Steve. If you had a working laser rangefinder, how would the final phases of landing potentially played out differently? Would you have been able to recognize you were approaching an area of a higher elevation and adjusted the landing appropriately so that you would touch down more softly, or would the slope of the landing area have made it difficult to land anyway? And then also, we heard on Friday about the Herculean efforts you made to incorporate the NDL data into your software. Did that not help on the final phases of the landing? How did that play out? Thanks.
Yeah, great questions, Jeff, and I'll try to be brief because Nilofer's asking me to. If we would have had the laser rangefinders, we would have nailed the landing. We actually have a terrain map built in to the system that anticipates the terrain we're going to fly over. It is robust to variations in that terrain. We've tested it for robustness to make sure that if we're off a little bit, it doesn't throw us off, and then it converges at the landing site. I'm confident if our laser rangefinders had been integrated in the system, we would have absolutely hit the bullseye. With respect to the NDL, what we had done, we absolutely succeeded in wiring the measurements in to the laser rangefinder registers. We absolutely succeeded in remapping the geometry of the laser rangefinder laser beams to what the NDL laser beams were. And we did all of that in the navigation algorithm. The part we missed was there is a data valid flag that's set all the way back in the laser rangefinder itself, and we needed to populate that in the navigation software that we patched to basically hard code it to 1. And because we missed that, the navigation algorithm said, you've got measurements, but I don't see my data valid flag that I'm expecting from the original laser rangefinder. So those did not process after all. So basically we landed with our IMU and our optical navigation data flow algorithms, which were unique. It's the first time anybody's flown this algorithm, and it exceeded expectations because we lived to tell about it.
Thank you for that, and thank you for your brevity. Next up, we have Adam Mann with Science News. Adam?
Hi there. I guess this is a question for Steve or Tim. Would you say that the lander has performed about what you expected, or has it kind of like exceeded what you would have hoped by this point?
Well, I think we'll both answer with as brief as we can, Tim. So, this lander has exceeded all my expectations of how it was going to perform. When we look at the systems today, nothing broke. The landing gear was subject to an environment that it was not designed for, a harsher landing that was outside its design limits. Everything on the spacecraft worked. We had single string items, we had redundancy, dissimilar redundancy, we had all kinds of protections that we could put in place within the limits of our schedule and budget. But man, this was a very robust lander I'm very proud of. And the little bit of a wire issue here or a little enable switch over there, those minor things are easily corrected. But when I think of major redesigns, we're thinking about adding cameras and adding antennas, things like that. But really a robust, I think somebody called it a beastly lander.
Yeah.
Scrappy little guy.
Scrappy little guy. Absolutely, Odie exceeded expectations in every effort, every area. And one thing I would add to that is our operations team and what they had preloaded in for how to use this machine on its way to the moon and how to command it and to respond to different conditions was masterful. And the vehicle responded to all of those commands. It responded to every demand we put on it well above expectations. And so it set the bar high for IM2.
Thank you so much for that. Next up, we have Leonard David with Scientific American magazine. Leonard?
Yeah, thank you. Maybe for Steve, I love the term overconstrained led to innovation. Maybe you could break that out a little bit. And I'm curious about IM2 as far as the launch date, what you see, and how would you gauge that particular landing area, Shackleton Ridge, compared to this? How would you gauge the difficulty for IM2?
Okay, so on the first part is you know, there's a lot of organizations that have an innovation officer or have innovation initiatives, and I'm not quite the believer in that. What I see firsthand from this effort of trying to go to the moon and return the United States to the moon for the first time in 50 years is that the innovation came from being absolutely over-constrained, where you didn't have enough time, you didn't have enough money, and you were trying to tackle a problem that seemed almost intractable. And so, with that said, we put a culture in the company of Intuitive Machines that there is no giving up, there's only perseverance, and there's only losing if you give up. And so find a way around it. If you can't test it one way, you have to test it another way. You can't have an unlimited budget. And knowing those constraints, you have to run lean and with agility, and innovative ideas come out in the form of all kinds of inventions and techniques, just like how we produced this one-of-a-kind, brilliant LOX methane injector for our main engine. We were able to get to a process where we produced a power head for the engine and injector every 10 days. And then test it on the stand. We 3D print it in 5 days, post-process it in the machine shop, get it on the mobile test stand, and fire it, and characterize it in 10-day increments. We were able to build 40 injectors in the period of time that we needed to build that engine and make it fly. And you know what? It flew perfectly. So that's an example. And I think there's a whole case study to be done on how we've done this lean, agile development that could be quite disruptive to aerospace in the way we've set the bar for a new price point for going to the moon and opening up the cislunar economy. The other one for Mission 2, I have so much more confidence knowing that the flight control, the propulsion system, and in fact, these algorithms, navigation algorithms that Tim talked to, can put us down in an area of craters and shadows, and they can put us down with precision. And that precision is what's needed if we're ever going to get to the South Pole. The fact that we had this trial run to the South Pole region, and we did it without a laser altimeter, only gives me confidence that when we put those laser altimeters in, we're going to stick that landing.
Thank you so much. Christine Fisher with CNN. Christine?
Thanks, guys, and congratulations, everyone. Steve, 2 questions for you. First, can we get a quick update on Eagle Cam? And number 2, when I interviewed you before launch, we talked about the competition with China, and you said, you know, I don't think that all competition is bad. I'm curious how you view this moment in the context of that competition, given that you just landed a spacecraft in the same area where both NASA and China have stated plans to build a lunar base. Thanks.
Well, number 1, with respect to Eagle Cam, what an amazing team of faculty and students at Embry-Riddle Aeronautical University who put their heart and soul into an ejectable camera that would come off of our Nova C or Odysseus lander and eject to the surface. Unfortunately, we couldn't get to that with the power descent the way it happened. And so this morning, I think it was this morning, as we went to each payload to try to reactivate them, we were able to reactivate the Eagle Cam. We reset the vision processor unit, powered up the Eagle Cam, and were able to eject it. And it ejected about 4 meters away from the vehicle safely. However, either in the camera or in the Wi-Fi signal back to the lander, something might not be working correctly. And so the Embry-Riddle team is working on that and wrestling with that to see if there's anything they can do. I think it's a wild success. I would love to fly the Eagle Cam again. Those students put their heart into it, and it's a really innovative design. And if we can get a picture of a landing, I'd love to give it to them. So we'll see what happens going forward with that. With respect to competition and the geopolitical environment, it's good to be first, and it's good to be on the surface in the South Pole region. And I think what it is all competition is not bad. Competition, in fact, when you can go put your resources to bear and you can go try and step in the arena and try to succeed at something that's very difficult, and then come out of that feeling the triumph and achievement of success, that's winning, and that's what the United States is all about.
Thank you for that. Rich Trubeau with the Orlando Sentinel. Rich?
Actually, I was going to ask about EagleCam as well, but Stephen, would you say you'd be able to fly it potentially on IM2 or IM3? And we'll just leave it at that.
Well, I'm not sure exactly when. I'm not sure whether or not the university can do it. It would be nice. We'll talk to them and see. I called Jim Gregory, the dean of the College of Engineering, and told him that give the students a pep talk that they built a piece of flight hardware, flew it to the moon, and ejected the camera. That's a success. Now, can we get an image? Let's work on that. And so we'll see how that plan shapes up over the next coming months and see where that EagleCam might lie in the future.
Thank you so much for that. Next up, we have Irene Klotz with Aviation Week. Irene?
Thanks. For Steve or Tim, when did you realize that you had made the landing without the LiDAR data? And what was the last payload to send back science data? Was it the Scout mission that you were referencing earlier, or one of the commercial payloads? Thanks.
Yeah, as Steve mentioned, we had a planned telemetry outage as the vehicle turned, and we went from one set of antennas to another. So we had not yet seen any of the LiDAR information at that point, but that wasn't necessarily a surprise because we weren't sure what the performance of NDL would be, and we didn't know if it would work until we got closer to the surface. It really wasn't until after probably day 3 on the surface where we began getting telemetry packets down and interrogating the stored data on the vehicle that we realized we hadn't processed it and we'd landed just with the optical measurements. There's a second part of the question, but I lost it.
What was the last payload?
Last payload. It's a race to the finish. We have, I think, Rolsys and Scalps have been generating and collecting data over the last 24 hours. And so who actually collected the last data and who generated the last data would probably be one of those, right, Sue?
Well, and it's also what data has been sent back latest. And what I can say is that as we were getting ready for this press conference, they're still running the vehicle. And so stay tuned because Odie's not done.
Great. Thank you guys so much for that. Next up, we have Ken Chang with the New York Times. Ken?
Hi, thank you. I wanted to confirm all the communications has been through the low gain antennas. And I was wondering if you could just describe how many there are and where they are in the spacecraft. And then I have some power questions. When is lunar sunset? When's the next sunrise? And how long do the batteries last when there's no more power being generated by the panel? Thank you.
Yeah, thanks, Ken. There are 4 antennas on the vehicle. During transit, we actually used our high gain antenna several times, as intended. But we have 4 Hemis on the top of the vehicle, and they all have a slightly different pointing, kind of like this. I'll get a better model next time. But they all point in slightly a kind of a clocking configuration. But those are all the Hemis. And then the high gain antenna is on this side, and it's co-aligned with one of the hemispherical low gain antennas. Since we've been on the surface, all communications have been with the low gain antennas, absolutely. And then for power, Odie runs about 125 watts, kind of in the minimum power mode for the computer and the radios and the power distribution units and minimum heaters. So once and it's not exactly sunset that's the problem, it's the sun is now passing across the solar array that we have available. And so when the sun moves past that, it'll be just a matter of a few hours. And we were getting really close to that when we came in. Now, the good news is, as you look at the way Odie's laying on the surface, the sun is moving towards the engine this way. And so by tomorrow, it'll almost be completely over the engine. So even though the lander is still illuminated, this particular solar array is not. But when the sun comes back up in the east, we'll find out if everything else still comes on. That top deck is in a great position to pick the sun up at sunrise. And so we'll start listening at sunrise at our location and see if Odie wakes up from a nap.
Thank you so much for that. Jim Siegel at nasatech.net. Jim?
Hi, everybody. Jim Siegel here, and thank you for taking my
question, and congratulations to all of you on a great success. I wondered if you had any idea what the approximate temperature on the lunar surface is, where Odysseus is, what the temperature is, and how would you rate the performance of the Columbia blankets that were supposed to protect the tanks for the propellants? Thank you.
Well, it's been cooling because the sun, even though we're at 80 degrees, it's starting to go down. And as you know, there's an intense thermal gradient at the moon, where things that are on the day side of equipment get very, very warm, and the things that are in shadow, even a few feet away, get very, very cold. And so, but the average temperature we are starting to drop and cool. That's very interesting because as we continue to record radio frequency data from our stations, listening to the last communications on this round with Odie, that's actually giving us information about multipath and the interaction with a cooling surface on the moon. And then as far as Columbia goes, the material has worked so well that we plan on using additional Columbia materials on IM-2. So this has gone from being an intriguing partnership for sponsorship to a relationship that is really valuable for us. And we're going to take their material technology and capability with us on future missions and expand on that partnership.
Great, thank you for that. Anthony Leone with Spectrum News. Anthony?
Hello, yes. Thank you very much, and congratulations on the successful mission. How much of the data that's been collected will be shared with NASA for their Artemis 3 mission? Thank you.
I think I can take that one. Definitely a suite of instruments that we have are very well designed for helping to ensure the safe landing of future Artemis missions. So the short answer is all of the data that can be used for Artemis will be used for Artemis. In addition, the science data in general, when NASA has payloads, the science data is archived in the Planetary Data System, PDS, and so the data that can be archived in there will be archived for this and all other missions as well. So that's something that generally happens in about 6 months after a mission is complete.
Thank you so much. Austin DeSisto with Everyday Astronaut. Austin?
Good afternoon. As many of others have said, congratulations. Thanks for your transparency throughout this. I'm really curious if you could talk a little more, either Steve or Tim, on kind of the data downlink limitations that have been, due to only using the low-gain antennas, and how that differs from, A, what you would have expected, and B, what you are expecting for IM-2 and IM-3. And furthermore, you said you want to add more cameras. Are we talking, could we see any high-resolution videos if that downlink capability is there? Thanks.
Well, from a communications point of view, once we landed, before we figured out how to configure our radios, we were getting drops of data. And then we moved from drops of data with the assistance of the large dish in Australia to a trickle of data, a steady trickle of data. When we land with our high-gain antenna, and we have an even better high-gain antenna on IM-2 than we had on this one, that will be a flood. And so it will be orders of magnitude more data at landing for IM-2 and beyond. And we have every faith and confidence that data will be there for us. So we're really looking forward to landing in that configuration. Now, with respect to beaming live telemetry and bringing that down, we're working towards improving that. That's part of the reason we're developing orbiting assets to have relay and communication services around the moon. It's very difficult to transmit on the fly, if you will, and get that all the way back to Earth with a high data bandwidth link. So our strategic plan is to eventually close that link by doing a bent pipe through orbiting assets. And then we will be in a world where we're seeing live video as we land. And of course, that sets up not only for safety for astronauts in Artemis, but more insight into the activities that are going on a day-to-day basis on the moon.
Robert Perlman with Collect Space. Robert?
Thank you, and congratulations. To Steve, while realizing that your primary focus has been on analyzing the landing data and collecting science, given that you know exactly where Odie touched down via LRO, has there been any discussion among the Intuitive Resources team, Intuitive Machines team, about nicknaming or proposing a formal name for your landing site?
I love that idea. I think we need to think about that. I'm going to start a competition for that. Anybody have any suggestions?
I thought Penelope would be a good one because that was Odysseus' wife that he struggled through all those voyages to get back home to. But we'll compete it just as we did Odysseus.
Thank you for that question. Leo Enright with Irish Television. Leo?
Thanks, Nilüfer. I was in that briefing room back when America last landed on the moon, and I can absolutely tell you that there wasn't a single person in that room who thought it would take 52 years. Anyway, my question, I think, is mostly for Joel, and that is to do with infrastructure. A boring question, infrastructure. How urgent is it to get infrastructure into orbit to support CLPS, not even the human landings, and how important is ESA's Lunar Pathfinder, which is due to launch hopefully fairly soon? How important will that be for the future?
Our Artemis initiative is a partnership with industry and with space agencies around the world. And what today, in these very initial robotic commercially provided service lunar landings, we buy each delivery of NASA cargo and our data back one mission at a time. But as you heard from, for example, Tim at Intuitive Machines, they have their own plans in place for what types of infrastructure to start deploying in cislunar space. Other companies do too. NASA in the U.S. really does want to explore the limits of service procurements and public-private partnerships as opposed to doing things ourselves. Part of that also, as you said, is taking advantage of partners' infrastructure development, whether that is technical demonstrations of infrastructure or actually providing infrastructure that all the partners can use. So as you said, on a future CLPS mission, the European Space Agency, working in partnership with NASA, will provide the Lunar Pathfinder COM relay demonstration node, and we will take that and drop it off at lunar orbit along with a NASA lander mission that will go down to the surface. As part of working these partnerships between NASA and other space agencies, we're looking at what type of science to do, what type of technology to develop, and what type of infrastructure is needed on the surface of the moon or in cislunar space.
Thank you so much. We have time for one final question, and we have David Curley with Full Throttle. David?
Thank you very much. Always fun to be last. Tim, I don't know if you were white in the face during the landing since Steve told you were going to land without lasers, and you did. But, Steve, it comes back to the switch in the one wire, and that changed everything for you on this mission. In the big picture, this is the first time you've flown, lot to learn. Are you humbled or emboldened by what you've just gone through?
Before the mission, we had an absolute sense of humility, yet relied on our technical excellence and trusted in our years of experience and this incredible team that we have. Following this, I would say, unqualified success of a mission, I'm emboldened. I'm emboldened for the future of the U.S. economy. I'm emboldened for the future of sustained human presence on the moon. And I'm emboldened for the future of Intuitive Machines and the wonderful team that we have, that we can be part of, a significant part of this new cislunar economy and pioneer our way forward. I'm really proud of that. And yes, I feel really emboldened today based on this success.
Great way to close us out. And thank you so much to everyone who submitted questions this afternoon and to our briefers for all of your comments and taking the time to discuss this groundbreaking mission enabled by NASA's Commercial Lunar Payload Services, or CLPS initiative. We hope that you continue to follow along on the journey by following Intuitive Machines' platforms or nasa.gov/CLPS. That will wrap today's briefing. Thank you so much.
It's a new era of pioneers, star sailors, thinkers, and adventurers.
3, 2, 1, 0. All engine running.
Let's go.